Hello everyone, my name is Arnaud Robert and I will be introducing you to our robust journey planning program. Say you have an important meeting. You use your phone to obtain an itinerary to the meeting. Would you like to know how safely you can make it on time? The answer is probably yes, and it will have you make some decisions. What path would you take to be on time to your target position? And given the choice between two paths, a shorter but riskier one and a longer but safer one, which would you choose? Our robust journey planning program will give you options to consider while making those decisions. Given some user inputs, our planning tool uses a static graph representation of the public transport network to execute a Dijkstra-based shortest path search, and finally conducts a posteriori confidence analysis to select the best itinerary options. Let us now talk into more detail about the graph creation process. In our problem, one of the constraints we face is the inherent time-dependent nature of the data. In order to conduct a vanilla Dijkstra shortest path search, we require a static graph and not a time-dependent one. Our solution was to not consider stations as being the nodes of the graph, but rather having nodes as combinations of a trip ID and station ID, inherently linking them to a specific time and place. Each edge can represent a transportation, walking, or waiting, and contains travel information, and it also goes backward in time in order to search from the arrival time given as input. A second constraint is the size of the graph, which can be quite massive. Thus, in order to alleviate the computational load, we only consider a subgraph corresponding to a time period centered around the time given as input. Michael will now talk into more detail about the shortest path search.
Thanks to the graph we made previously, we can basically use Dijkstra in its regular form pretty much immediately. But let's just first remind that Dijkstra in this case requires to look at neighbors that are valid and also paths that are doable in terms of time. And so our graph will show that our graph allow to use this Dijkstra by fulfilling those kind of conditions. So first of all, doable path. Let's consider two consecutive edges from S1 to S2 and S2 to S3. What we mean by doable is that the arrival time at S2 needs to be before the departure time from S2 to S3. And so the way we deal with it in our graph is that we really construct edges such that the arrival time on S2 is the same as the departure time from S2 to S3. And so what about the valid neighbors? Here in this case, usually people would consider station to be nodes, but then if we do that, edges would be time dependent. So in this case, in this example, for instance, let's say that we have a query at 2 p.m. but then the edges are only representing morning paths. So technically would still consider station 1 and station 2 to be connected, but it shouldn't be, because in this case, the query at the afternoon doesn't include any path, shouldn't include any path. And so in our graph construction, we use edges that link nodes, and these nodes are tied to a specific time, the edges as well, due to that. And we see, for instance, that if we do a query at 2 p.m., we would find a node from which to start, and on the allowed edges would also fit the time so that it's allowed as well. So now I'll just leave the handling delays to Quentin.
We use the data from the SBB dataset to gather real-life insights and to compute the positive delays, meaning that if a trip arrives ahead of schedule, we would consider it being on time. We then group this information based on the day, the hour, and the mean of transport, and then computed the probabilities for each of them to have less than X minutes of delays. We can see here that the probability for a bus to arrive on time on Monday morning at 8 a.m. is only of 37%. We can see here that buses have more delay than trams. This is in part due to the fact that they are more influenced by the traffic. To compute the confidence to make a connection, we retrieve the probability for the current trip to have less delay than the waiting time at the next stop. We can see here a full table with two waiting time of 4 and 8 minutes and 5 minutes to spare before the arrival time. We will then compute the confidence for each of them and multiply them to get 85% of chance to arrive before the given time. We will compute the final confidence at the end, which means that it will not influence the searching algorithm, but will only filter the path given by it. I will now let Alejandro tell you about the results.
Okay, so let's see the results of a search. So here we show you the solution of a search given this query. So we see that the probability to be on time of the first solution is very high because we only do one change and we arrive 6 minutes sooner than what we asked. For the second path we see that we need to change 2 times, and those changes we don't have that much time to do them, and we arrive later than the first one. So that's why the probability of the second to be on time is a lot lower than the first one. Here you can visualize the 2 paths on a map. So now let's talk about the pros and the cons of our solution. So one of the advantages is that because we are using a static graph, we can use vanilla path search algorithm like Dijkstra or Berman-Ford to solve a time-dependent shortest path problem. So that's very nice. However, this comes with huge drawbacks. Namely, there is this heavy pre-processing to create the graph and to perform the search. We have way more nodes than stations and a lot of edges, and this makes the graph just huge. And because of that, the query time takes in the order of minutes. So we are totally aware that there are a better solution, and that this can be certainly improved with a smarter approach. With this, we conclude our presentation. Thank you for watching.